Okay, so now let's use what we actually learned to do Markov Monte Carlo sampling, Markov chain Monte Carlo sampling. So before we had our silly little example of people moving countries, and I use that example because I think it's helpful to think of like ensembles of people moving. Um, as like and then probabilities is representing portions of ensembles. But um, here let's go and we need to think about it a little bit differently um, for the purposes of sampling. So I'm representing a little Markov chain that we might have here. So now the states of the Markov chain when we go into reference to Monte Carlo sampling and thinking about how we can do sampling in the first chain with a Markov chain, um, that's that states are going that like states of the Markov chain are going to represent states of our probability distribution. So for example, if we have a Gaussian, that would actually have a continuous state space because like the Gaussian can take infinitely many values. That shouldn't scare you though, because if you go and look at the form of the equation and how we're going to apply this, you're going to see it's really trivial to apply this to continuous distributions. Or another example in the case of discrete distribution, like if we wanted to sample from a distribution that was like, 1/2 state A, 1/4 state B, 1/4 state C, and we wanted to generate samples like that, we would set, or actually I'm going to use that as an example later. But so the stationary distribution will be the distribution we want to sample from. So let's just take that example I just gave. The distribution that we want to sample from would be, is basically having our stationary distribution be like, 1/2 being A, 1/4 being B, and 1/4 being C. And transitions will be, the transition matrix will give you the transition from one state to another. So, and the ensemble of all your samples should approach your stationary distribution. So this is really best. I think this is really best illustrated with showing an example, a particular example, and actually going through the algorithm. Okay, so let's say I want to draw samples from like this probability distribution right here, where state A would be 23%, state B would be 45. So I want 23% of my samples to be state A, 45% of the samples to be state B, and 32% of the samples to be state C. And so what we can do is, like, to do this, we can perform a Markov chain. So, this is how we do the Markov chain, is that we start here, we start in state A. Like we just choose a state to start at. And you can imagine, like, you're going to have to apply this in code. You can imagine that, how you would apply this in code. So you start at state A. And then what you do is that you propose another state to go to. You propose a state to jump to. And this is called, when you propose the state to jump to, this is called the jump proposal. And this was our psi in what we saw before. I think, yeah. So this was the transition matrix that we came up with. The jump proposal, as I mentioned in the last video, it's the psi. So like for our let's take a particular case that it might be a 1/2 probability to go to state A, and then a 1/2 probability to propose to jump to state B, and a 1/2 probability to propose to jump to state C. And let's say we do this and then we actually get that we propose to jump to state B. So now we're in state B. And now we actually have to decide if we're going to jump. So the decision to jump is given by this part of the transition matrix, this thing right here, where this part is, of course, the stationary distribution. This is the proposal to jump. So for our particular case, we wanted, you know, what like it's the probability to go from A to B. So like mu sub y, we want 45% of our samples to be, you know, in state B. So that goes there. It was a 1/2 chance to propose to jump to B. And then it's the similar thing for, you know, that's 23% of our samples we want here, and then it's a 1/2 chance to jump to, or sorry, it's a 1/2 chance actually, it'll actually be a 1/2 chance to propose to jump to state B to A. And that'll actually be, that is an important thing to consider. Yeah, but anyway, you plug in these numbers and it's not hard to see that, you know, these 1/2s cancel out. And this thing is greater than 1, so you just take 1. So it basically, for this case, if you propose to jump to state B, you're going to go to state B because it's going to be greater than 1 probability that you actually go. So that, you know, now we're actually in B. You know, and then we keep repeating this. So now you're in B, and you go through the same process of doing the thing of proposing a jump, deciding if you're going to jump, and then actually jumping or not. And what you do is that you record the list of where you've been, and that list of where you've been, that's called your chain. Your samples, those are your samples, and that chain, the portion of that chain, if you run that chain long enough, the portion of that chain that will be state A is that, you know, if I run this for like 1,000,000 samples, 23% of my samples will be state A, 45 will be B, and 32% will be C. And in that way, when you do that, you have successfully drawn from a distribution. You've successfully drawn from whatever distribution you want. But notice it's going to actually take some time for that entire chain you have to actually approach that stationary distribution. It's not actually going to be perfect. So yeah, it'll take some time for that to happen. But when that's happened, that your chain that you have goes to and approaches the stationary, like the stationary or the distribution you want to sample from, we say that the chain has converged. Okay, so that should give you, I hope, a good basis on Markov chain Monte Carlo, the theory, where it came from, and how to actually apply it and why it works for sampling. If you have questions, please ask.